Yo, what's up everyone? Welcome to the last part of thermodynamics. Today we're going to be talking about spontaneity and Gibbs free energy. So there's going to be certain types of reactions like the rusting of iron that are going to be spontaneous. If you leave iron outside, it's going to be exposed to water and oxygen, and when iron is exposed to water and oxygen, it forms rust, and that's the chemical equation there that happens, the chemical reaction that happens, and the product is rust. That's the chemical formula of rust. And so essentially, if you leave iron out, it's going to rust. And those are spontaneous processes. These are processes that favor the production of products under certain conditions. So there are going to be certain reactions that are just going to happen. As long as you leave them alone, they're going to happen. And one of these reactions is going to be carbon diamond turning into carbon graphite. So technically, all the diamond in the universe will eventually turn into graphite. But the thing is that it's really misleading. Thermodynamics doesn't tell us anything about the rate of a reaction. So although this reaction is spontaneous, although it's going to happen at such a slow rate that it's basically not going to happen. Like the amount of time it would take for a significant amount of diamond to turn into graphite is longer than the age of our universe. So thermodynamics doesn't tell us anything about the rate of a reaction. So how do we know whether or not a reaction is going to be spontaneous or not? In order to find that out, we need to look at something known as Gibbs free energy. Gibbs free energy is represented by delta G, and it's a function of enthalpy, which is delta H, temperature T, and entropy, delta S. So your Gibbs free energy is the enthalpy minus temperature times the change in entropy. And so that is our Gibbs free energy function. If your Gibbs free energy function is equal to 0, the system is at equilibrium. If it's greater than 0, you have a non-spontaneous process. If your Gibbs free energy is a positive value, that's non-spontaneous. If it is less than 0, though, it is going to be spontaneous. And so that's how you can tell whether or not something is going to be spontaneous or not by looking at its Gibbs free energy. And so we can look at Gibbs free energy in terms of the enthalpy and the entropy. Depending on whether or not your entropy and enthalpy are positive or negative, your reaction is going to be spontaneous or non-spontaneous. So what do I mean? For example, if your enthalpy value was negative and your entropy value was positive, then that means your enthalpy here is negative, and this value here, this whole thing, stays a negative. So you're taking a negative and you're subtracting something, so that value is always negative. This means that your Gibbs free energy is always negative regardless of what temperature you have. So that means you are spontaneous at all temps. Let's look at if you had a positive enthalpy and a negative entropy. This means that your enthalpy is positive, and this value is going to be positive. So you're adding a positive and a positive. That's always a positive, meaning your Gibbs free energy is always positive regardless of what temperatures you have. This means you are non-spontaneous at all temps. All right. Let's look at negative and negative. If your enthalpy was negative, your whole thing could end up being positive. This is because when you have a negative entropy, this value here becomes a positive. So if your temperature is high enough, then your entropy might make it become a positive. So in this case, at low temperatures, you're going to be at a negative Gibbs free energy value. So this is spontaneous at low temps. Last one, positive and positive. Your enthalpy stays positive, but your entropy could overtake the enthalpy if your temperature was high enough. So if your temperature is high enough, you have a negative value, so this means you're spontaneous at high temps. And you can see a diagram here, or the completed chart here, where you have all your combinations. So if you looked at your Gibbs free energy as a chart, if you look at something with a negative delta G or something with a positive delta G, let's look at negative first. In negatives, you start out with pure reactants being at high free energy, and then it goes down. So your change in free energy is negative, it goes down. In positive, your free energy starts off low and it goes to high. So you can see as it goes from pure reactants to pure products, how the free energy changes based on whether or not you have a positive or a negative value. The thing about free energy and a system is that a system always wants to be at the lowest free energy. For the situation on the left here, the lowest energy that it can be in is all the way when it's at pure products. This means that this reaction will go to 100% completion, because at 100% completion is when you reach the lowest free energy that the system can be in. And if you look at a positive delta G, the lowest free energy it can be in is when it's in pure reactant form. This is why certain reactions are just non-spontaneous. They won't happen because you've already reached the lowest free energy that it can be in when you're just in pure reactant form. Now, not all reactions are like these two ones here, where the line between them is linear. You're not always going to have a linear line. Sometimes it can be kind of slopey. So you can still have a negative delta G where your products are at a lower point than your reactants, but the lowest point in the entire reaction happens somewhere in between. It happens somewhere in between the reactants and the products. And if you look at a positive delta G, you can see that the reactants start below the products, but the lowest point is somewhere in between the reactants, between pure reactants and pure products. So this explains equilibrium reactions. This is why thermodynamically equilibrium reactions happen. Not all reactions are going to go to completion. Some reactions are going to favor being in some sort of intermediate form between pure products and pure reactants, and this explains thermodynamically why this happens. The system always wants to decrease its free energy, and there are points where free energy is minimized as long as you're between your reactants and your products. But you can see a difference between the diagram on the left and the diagram on the right. On the diagram on the left, you reach your equilibrium at a point where there's more products than there are reactants. But the one on the left, you reach it where there's more reactants than products. So we kind of need a way to quantify where a reaction reaches equilibrium. What position in how much products, how much reactants, and we turn that into a mathematical operation, and we just call it K. K represents our equilibrium constant. It's the position at which your reaction reaches equilibrium. If your K value is less than 1, your equilibrium favors the reactants. The reaction on the right here would have a K value of less than 1. There are more reactants than there are products, so your K value is less than 1. But on the other hand, if your K value is greater than 1, equilibrium favors the products. Your reaction on the left here would have a K value of greater than 1. That's because it reaches equilibrium when there are more products than reactants. So you can see how your equilibrium constant can be different thermodynamically and how that affects the Gibbs free energy curve there. Now, there is a mathematical way to correlate Gibbs free energy and your equilibrium constant, and it's this equation right here, where your change in free energy is equal to negative RT times the natural log of K, where R is 8.3145 joules per Kelvin times mole. And we have a problem here to kind of see how this equation works. So we're told that the KSP of barium sulfate at 298 Kelvin is 1.1 times 10 to the negative 10th. What is the delta G at 298 Kelvin for the following reaction? Alright, since this problem deals with a K value and we're asked for the change in free energy, we know that we're going to need to use this equation here. So delta G standard is equal to minus RT natural log of K. Although you might think you know K, you don't really know K. The K here represents the KSP. The KSP is dealing with this equation here, where barium sulfate solid is turning into barium 2 plus aqueous and SO4 2 minus aqueous. That's the reaction that this KSP represents. The reaction that we have is in fact the opposite. The K value that we want here, if you wrote out your equilibrium expression for this reaction here, it would be 1 over barium 2 plus and SO4 2 minus. Remember, your equilibrium expression, equilibrium constant, is just your products over your reactants. But in this case, since your product is a solid, solids don't count in equilibrium expression, so you don't include them. So our K here is this value right here. How do we find our K value from the KSP that we're given? Well, since the KSP represents this reaction here, the KSP is going to be equal to the concentration of barium 2 plus times the concentration of SO4 to minus. And we know that this value is equal to 1.1 times 10 to the minus 10. And so this Ksp value and the K value that we're looking for is really similar. If you look, the K value that we have here is just the reciprocal of your Ksp value. It's just 1 over your Ksp. And so that is 1 over 1.1 times 10 to the negative 10th, which is 9.09 times 10 to the 9th. That is your K value of this reaction here. And we found that by flipping the Ksp that we're given. And so now we can plug everything into our equation. We know that delta G standard is equal to minus RT natural log of K. So that's minus 8.3145 joules per Kelvin times mole times the temperature, which is 298 Kelvin, times the natural log of K, which is 9.09 times 10 to the 9th. And if you did out all this math, it would get you about negative 57,000 joules per mole, which is negative 57 kilojoules per mole, which is answer choice A. And that is your answer. So yeah, that's how you relate your equilibrium reactions to your Gibbs free energy. I hope this video was helpful. That's all I have. I hope you learned something, and I hope to see you later. Thank you.